Hi, good morning and good afternoon to all of you. Thank you very, very much for attending this webinar. Very pleased to be speaking today about knowledge graphs. So just a little bit about myself. My name is Petra Selmer. I'm an engineer on the Cypher features team at Neo4j, and I'm also a member of the Cypher Language Group. And the Cypher Language Group is essentially the group at Neo4j who participate with other vendors and researchers outside of Neo4j, where we actually define new features that make it into Cypher at some point in the future. So if there's some new functionality that Cypher should be allowed to do in the future, we're actually the people who decide how that should look like, what the semantics should be, etc. Right, so without further ado, I shall just walk you through the agenda very quickly for today. So what I'm going to do is begin with the property graph data model. And so it's very, very likely that most of you will know about this, but I'll just give you a quick tour about this anyway, because it's very, very relevant to the rest of the talk. Then I shall also just give you a very quick introduction to Neo4j and a couple of the use cases. Then we shall actually dive into the meat of today, which is all about knowledge graphs. So I shall begin by just going through a few preliminary slides setting the scene, essentially. Then also I'm going to try and define to you what our definition of knowledge graph is, also how we envisage this working within Neo4j. And then I shall round that section off by talking a bit about the tools and techniques to actually, first of all, manage your knowledge graph, and then how to actually use your knowledge graph effectively. And then we shall be ending the talk off with a really super case study, and that's the eBay ShopBot. So to begin with the property graph data model, so essentially this is comprised of three constructs, if you like. So the first is a node, and that essentially is any entity of interest in your domain. So this can be a person, it can be a car, a building, etc. A relationship is then a connection between these nodes. So a relationship, for example, can model the fact that a person lives in a building, for example. And then both nodes and relationships have characteristics, attributes, or what we call in the property graph data model, a property. And these are essentially key value pairs, where a key can be, for example, a name, and a value can actually be the actual person's name. Further extensions to the property graph data model include the following. So we can actually have that a node can have 0 or more labels. So a node, for example, can be a person, or it can be a person and a teacher. Also, a node need not actually have a label, although we find that that's actually a very odd thing to do, because that actually means you lose a lot of the meaning in your graph. We then have the fact as well that a relationship absolutely must have a type, and that's one and only one type. So a relationship can be things like knows, likes, etc. And a further rule, if you like, is a node or relationship may have 0 or more properties. And once again, if your node or relationship has no properties at all, that's a very weird thing to do. But you know, if that's something you really, really want, it is possible to have that. And this again is just drawing out very visually. So of course, graphs are a very visual thing. This is drawing out very visually what this actually looks like. So here we can actually see that we have two nodes exemplified by Dan and Anne. Both of these nodes have a person label. Both of them have a name property. So the first node obviously has Dan as the value, and the second has Anne as the value. And they're actually joined by a relationship with a type of knows. And essentially melding all of these things together, you actually very quickly can get into a very rich description of a domain, and by just looking at this, even though I haven't described to you what this graph actually does, you can actually very quickly see in there what's actually going on, the flow of connections, and essentially what you can get from here is the context, which is very, very something very much graphs allow you to do. So for those of you coming from a relational world, you may be asking yourselves, you know, why graph? Why not, you know, why not relational? And essentially these are, if you like, this is the crossroads. We've got discrete data problems. So if your data is pretty much rows and records in a table, or I should say rows and columns in a table rather, and where the connections between tables don't matter too much, a relational database actually does the job very, very well. And of course, we've got the well-known and well-loved SQL query language for that. However, in cases where your data is very much starting to resemble a connected data problem, and in fact we're seeing more and more of that across all our vertical sectors in the last few years, those connections are starting to matter just as much as the actual data elements themselves. That's possibly where a graph database would certainly be a much better fit. And the query language we actually use, and in fact I'm going to talk about that a lot more later on in this presentation, is called Cypher. And very easily, very quickly there, you can actually see that it's a pattern matching language. So it's all about how to transcribe a pattern between nodes and relationships. As I say, I'll talk about that more later on. So I'll just very briefly introduce you to Neo4j. So who are we? And essentially the answer to that is we're a graph platform for connected data. So at the heart of Neo4j, of course, is the property graph database, and we do all sorts of good things around there. We ensure that we are very, very performant out of the box. We ensure that we comply with ACID rules with respect to our transactions. That is to say, we absolutely ensure that if you commit a data item to your graph, it will actually be committed. So your data is very, very safe. There's no worry to be had about losing your data or corrupting your data. We take a lot of care to ensure that your data is safe. We also ensure as well that the product is easy to use. So Cypher is a part of that. We also have other tools as well, though, just to ensure that developer productivity keeps rising and rising. And around the actual property graph database, we've now extended that to this idea of the Neo4j graph platform, and essentially you can now see around it there's a lot more going on. And that is essentially what we're trying to do is drive relationships as a first-class citizen and the use of graphs beyond developers. In the last 2 years, pretty much developers and DevOps people have been our focus. We're actually trying to shift that now beyond that community to also include other facets of organizational structures, such as maybe the business intelligence environment, data analysts, data scientists, etc. We also are now ensuring that other facets such as visualization, graph analytics, such as whereby you can perform algorithms, such as cluster detection and PageRank, all those very, very graphy things, that they're also brought into the mix as such. And the idea around this is that these other non-developer personnel, I suppose, that together we can actually get a more robust perspective on your data that you may not get if you actually use traditional analytic methods. So this is an evolution. Just to briefly mention to you as well something about our two of our customers. We've got many, but these two certainly stick in my mind. So the first one is the NASA use case. So they're actually using a knowledge repository stored in Neo4j as a foundation for mission history databases. So essentially what they've done is they've taken all the knowledge of every launch over the past 40 years. So you can imagine that's quite a lot of data. And they're actually storing the Neo4j. And the idea then is in their current upcoming launches and missions and research, what they can actually do is they can trace back situations where problems occurred in the past. So previously it used to take them quite a long time to actually trace through various tables and records of what went wrong in 1972, for example. Now they're actually finding it's a really, really easy way of actually finding out very quickly things like root cause analysis and maybe finding out alternative configurations for various components, that sort of thing. And they actually had a fantastic talk at Graph Connect, so I do urge you to look at that. And I think the takeaway message was that that saved them about 2 years' worth of research into the decision-making process. So that was actually, that's quite cool, we think. The other customer on our right is, of course, the Panama Papers. They actually won a Pulitzer Prize earlier this year. So probably this needs no introduction. They've been in the news a lot. And essentially, this is all about tracking where money was flowing. So, of course, this is the leaked data from the Mossack Fonseca legal entity in Panama. And essentially, many interesting investigations came out of that and many newsworthy items. And actually, very recently, I'm sure you've also noticed that we had the Paradise Papers situation as well. So that's basically continuing in the same form. So if you like, it's the sequel to Panama Papers. So what they've actually done is the journalists have added data from the Paradise Papers to the Panama Papers and are now building up an ever richer and richer context. So that's also apparently an ICIJ have told us that's an ongoing investigation, and so revelations will keep coming, so keep your eyes peeled. And for Panama Papers and of course Paradise Papers, the core underlying technology is Neo4j, and also they've partnered with people like Linkurious for the visual aspect, and that's so that the data is described in a visual way so that people can navigate and understand how these entities are connected and what's essentially going on. And here is just a snapshot of some of our other customers. So as you can see, we pretty much span the spectrum all the way from software through to health. And also what's actually not on here, I think we also have quite a lot of interest from the academic sector. especially in terms of bioinformatics. So that's actually growing and growing. So just to end off with maybe a bit about why we're actually succeeding in this space, and I think very core to this is the fact we've got an open source business model. So for many years now, we've actually been running a range of events and training, reaching out to developers in the community. What we also did a couple of years ago, although we perhaps haven't publicized this as much, but we are certainly trying to do that now, is we started the openCypher project. So as probably some of you know, Cypher is the query language developed at Neo4j for property graphs. And the idea is we thought, well, it's such a great query language, we'd really, really love it for other vendors and also for researchers to use it as well. So we've actually opened up Cypher. So essentially anybody can now go to the openCypher.org website, and they can actually, from there you can go to our GitHub repository as well. And what you have there is you've got access to our grammar, you've got access to our technology compliance kit, you've got access to our documents, so anybody can actually implement Cypher. And in fact, that's actually what's been happening. So I've listed there for you a few of the commercial vendors. So SAP HANA, for example, is using Cypher for their graph matching portion of their systems. Redis Graph as well, MemGraph and Agents Graph. So the latter is actually an implementation of Cypher on top of PostgreSQL, which is very, very interesting. We've also got a number of research projects as well. So in fact, we're starting to go to more academic conferences, and we're seeing more and more that where graphs come up, and believe me, they are coming up much more than they used to in the past. And when implementation is involved, Cypher will play some part in that. So, and very, very excitingly, I think about a month or so ago, we actually released our first implementation of Cypher, which does not run on Neo4j, and that's actually our CAPS project. So standing for Cypher for Apache Spark. So if you're interested in that, please take a look at that link I sent you over there. It's an alpha release, but essentially what's actually happening is we've turned Spark and its great in-memory calculation capabilities into a graph traversal and graph analytics environment, and we're using Cypher to actually manage your graphs within Spark. So very, very exciting news there. And also a couple of the other things. So for example, we've always been very much committed to data safety, data integrity, making sure you don't have data that cannot be trusted. So now to what knowledge graphs actually are. So what I'm going to do is just begin with a bit of a preamble to just set the scene, so to speak. So first of all, graph databases are used in quite a lot of vertical sectors, as I'd alluded to previously. So here are a few actual examples. We've got things like recommendations, and these are, for example, used by retailers, and also pricing recommendations and that sort of area. Fraud detection is a lot about detecting the flow of money, understanding how the money actually flows, is anything suspicious going on, etc. A lot's also to do with network management, and this has quite a few flavors, but I think the one we've seen the most would be root cause analysis, and also say within a data center, which component is most dependent on, i.e. if that component goes goes bang, it's not a good thing. What we also have here is a few other sectors, but what we actually don't have on the screen are things like pharmaceuticals, where they're doing a lot of work around drug repositioning and drug discovery, and also healthcare and bioinformatics as well. They really, really are finding the utility of graphs very, very useful. So just to give you, again, a visual sample of what these look like, here are a few sort of graph shapes, if you like, based on various domains. And now we come into actually what problems occur out there. And probably have actually, I would say, have occurred for the last few decades, but only now we're actually able to perhaps find solutions to these problems. So I'll just very, very quickly walk you through. So first of all, what problem exists? And this is that the organizations have huge difficulty in maintaining their corporate memory, if you like, for a variety of reasons. So first of all, obviously a business to be a healthy business obviously needs to continuously grow and evolve. And this obviously presents new gaps in the knowledge and challenges. We also obviously have turnover, where long-term knowledge may actually disappear from the organization. And also probably something that I'm very familiar with in my previous places is aging infrastructure and very, very siloed information. So there could be great nuggets of information somewhere, you just cannot get to it though. So what are the consequences that may arise from this? Well, pretty much, I think the biggest one here for me certainly is the one I've highlighted, and that is you don't actually know what you don't know. And furthermore, you don't actually know what you do know. So the idea, graphs actually are, I think, one of the great way to actually bring these gaps, if you like, to light. They also reveal connections leading to new insights. So essentially, the other negative consequences are, obviously bad information is a very bad thing to have, and also, yeah, maybe staff are not able to capitalize on good opportunities that may arise, lack competitive advantage, slow down. So the idea is basically knowledge graphs. So I've actually sketched out for you over there a picture of what this is going to start to look like. So what I'd like you to focus on here is the fact that we've actually got various data silos. So each of these areas, if you like, have their own database, and actually the idea is, a knowledge graph is to actually join all of these up together, and that's actually essentially the idea for the rest of this talk. So I'm going to actually walk you through a step-by-step definition of what I think a knowledge graph is. So the idea is that what we're doing is we are enriching a graph, and I'm going to talk about how you may enrich a graph a bit later on, with more and more data, either raw or derived over time. And that means you actually get a graph that's even more detailed, has even more context, has truth. By truth, I actually mean that the data is correct. So maybe the original graph had data that was, perhaps not 100% verified to be absolutely correct at the time. But as the graph evolves over time, the idea is that your data becomes more and more correct. So maybe there are processes to actually verify that a certain fact stated in the graph is true. Also, as the graph gets more and more detailed, we get more intelligence imbued in the graph and semantics. So all of this is pretty much driven by the fact that having a relationship as a first-class citizen, so that actually gives you all of these great things. Also, what I should actually mention is that a property graph database does have a schema, but it's optional. So the idea is also that your schema can evolve over time. So maybe you begin a graph without any schema at all, because you just have no idea what the shape of your data ought to look like. But as your graph develops over time, maybe certain truths start to emerge, and you can start to encode that within a schema. And then as time goes on and on, you actually can start making that a lot more stringent. So having this great graph that's been enriched, what it essentially is doing is capturing the real world, and that is what I really mean by that is it's capturing your particular domain, the domain being what you actually decide is important to you, and it's capturing that much more precisely and much more comprehensively. And what this means as well, it's all very well having this great graph, and it's it's rich, it's got true facts, etc. But if you cannot actually search for that, get information out of it in a meaningful way, that's not going to end very happily. So very, very a pillar of this is basically that the information needs to be searchable. And the idea, of course, out of all of this, what we all want out of this process is that knowledge comes to us, and that's both directly, so maybe things you're actually searching for that you want to actually find out, but also indirectly, and these are maybe those things that you didn't know, etc. So actually new insights are discovered in a very serendipitous way. So that's sort of my take on what a knowledge graph is and the process to actually build it up, and also what we really want from knowledge graph at the end of the day. So just to maybe summarize very quickly is they essentially provide a 360-degree view of any entity of interest. Again, if you're in the sales sector, maybe these are customers, products, sales, purchase orders, those sorts of things. Also auxiliary entities, maybe it's stores at which customers bought products from, those sorts of things. And also the processes that surround these. So maybe it's the way that shipments are handled and fulfillment processes and all that sort of thing. And I've also transcribed for you below an example of what they may look like. So essentially, again, just to drive home, I suppose, is that knowledge graphs can really give answers about things it knows about, but also very importantly, and I think very usefully, especially going forwards into the future, explain why and how the answer was returned. So it's great knowing something, but you maybe want to know, why is this the case, and what other facts led to this being the truth. And then again, we can actually get from the context and structure within the graph. And as I said, just to really, really drive home this fact, they must be searchable. And as I say, I'll cover that more later on. So I'll just give you a quick overview of how we envisage this working in Neo4j. So the idea here is there's quite a lot going on here, but I'd like you to focus on the AI workflow loops. That's just that circle in the left-hand part of the screen. The idea here is that we've got a developer building a system, say like a recommendation engine or something like that, and that's all very well. But as that system gets used more and more, it becomes thirsty, if you like, for yet more data. So ideas that actually adding more knowledge to that graph upon which that application works would be a great thing. And the way it's done, and that this is the idea of the graph platform, is that a lot of the information that comes out of that application, plus other applications within the enterprise, gets put into a data lake or a data warehouse. And the idea is that we'd have data scientists going through that data and actually coming up with new algorithms to actually, you know, the need for new algorithms is triggered by this rich data coming into the data warehouse. And the idea then is that these algorithms would then be fed back to the developers to incorporate within the application. And so this is a feedback loop, basically. The data being added drives the need for more algorithms, then more algorithms get developed and fed back, feed the intelligence of the graph becomes richer, and so on and so forth. So hopefully that cycle is quite clear. So essentially, as time goes on, this is how that graph, that original graph, gets enriched and gets imbued with extra intelligence, essentially making it much smarter while it's operating. The idea then is also that across the enterprise, the other people, i.e. analysts, business users, also the CTOs, the compliance people, etc., would also then have a need for some of this knowledge to get through back to them, so that the business drivers then become more aware of the connectedness of the data and can go forwards into making better decisions based on this. So what we have here basically is, just to walk you through an example, is two sets of, at this moment in time, fairly disparate information. So what we have actually are two different business processes. One is products, and actually how to show the product and get customers to buy them. And the one on the right-hand side is all about the customer and user journey after the purchase. So, so how their purchases happened, what their shopping cart was like, what reviews they may have given regarding the product. So here actually, while these things are in these sorts of silos, it's quite difficult to obtain a cross-section of what, why did a customer buy the product in the first place? And what did they feel about it afterwards? Are they likely to return? These sorts of things. So it's, at the moment, it's quite fragmented and hard to get the story. So temptation may actually be, and this certainly works up to an extent, is actually to put all this information, all the way from purchases through to views, through to shopping carts, into a data warehouse or a data lake. So it's an idea of, yay, let's consolidate that knowledge on a vast scale. Let's just, dump it into the lake. And then, you may actually use a core set of tools and, Hadoop, Spark, Elasticsearch, etc., to actually undertake and to write business intelligence applications so that that information can somehow be consumed. I think that's great up to a point, and that's simply because a lot of this data may be unstructured. So there's no way of actually pinning down what the entities of interest are. It could be quite a difficult and slow process as well to get information out of that. So essentially, the format's not necessarily great for putting into action, or being able to draw out actionable information, or being able to derive insights on the fly. Also, these processes could be quite slow as well. So what you do is you actually lose that operational nature as well. So how do we go about solving this? And what we've actually started to see more and more, and this is the knowledge graph story, is essentially just take relevant pieces of data out of the silos. So you take the bits of purchasing information out of your purchases database, relevant parts of your product catalog out of the document store, etc. And you actually materialize them as graphs into one large super graph, up, as you can see in the middle of the screen. And essentially now what we've done is we've stitched together all the various facets of the information. And this is essentially what our platform environment provides. We actually also provide the capability, for example, to take relational data out of a database, and to actually materialize it into a graph. And the way you actually do this is you can define how a relationship in the relational database needs to be materialized as a graph. Also, if you take a table, that will generally be transformed into a node. So you actually would probably label the node with the name of the table and select which columns you want, and then those will be transformed into properties, that sort of thing. So we actually do have tools to allow you to do this. So the idea is now that with this larger graph that gives you this cross-sectional view of all of these different informational facets, you can actually now query this graph in real time, and this brings you back into the operational mindset. So just to again walk you through from a slightly different point of view, here what we have is we've got three very distinct graphs. So we've got a customer graph, a product graph, and a supply graph. And the idea, of course, is to join all of those up. And what we now actually have is no longer a customer graph and a product graph and a supply graph. What we actually have is the knowledge graph for that particular organization. And the idea is that this data gets built up, it gets enriched over time. And what this actually means is that because you've got this joined up view and you've got maybe information about, in the far right-hand side of the graph that can actually affect information in the far left-hand side of the graph, you can start adding different information that wouldn't have been obvious to add if they're still in their original data silos. And so what you could actually do, for instance, in this particular use case, is that you can start to perhaps identify and then materialize all your different types of customers, as well as maybe different types of buying patterns and that sort of thing. And what you can then start doing is extra things over and above just selling and recording user reviews and that sort of thing. So for example, what you could actually do in here is, because you've now got the graph enriched with customer information, you can start to record what their normal buying patterns are, and if there's any deviation from that, so you're starting to think that maybe Fred Blogs has some funky fraud going on with his credit card, you can actually start flagging that sort of information. You can actually maybe also start to identify different members of a family, so all of that information can also be evolved and persisted. And also maybe what you can do in this particular case is, if you hook into, because we actually would also be maintaining the address information, and say if you hook into another source that gives you weather updates, say you could actually tell Mary Jones that her order that should have arrived this afternoon will now be delayed because of a hurricane approaching or something like that. So you can really start to be much more responsive to customer demands and also to alerts and things like that. So you can start really bringing out lots and lots of information. So the goals basically are that the idea is to have this very rich context, meaningful repository from which to store and draw institutional knowledge. And essentially the idea is that if a corporation who maintains such a knowledge graph will basically always be one step ahead, that they're not going to lag behind or get bad information. So what's required to get there is essentially it's all about data integration. How do we integrate diverse data sets? And how to maintain those connections, how to actually do these things. So again, you're going to need to use a variety of tools like natural language processing, Elasticsearch, and of course graphs underpinning everything. And very importantly, as I've mentioned a couple of times already, is the information must absolutely be searched for, because we need to get that information out. So the idea, if you like, before I end off this section, is that you may actually end up at the point where a knowledge graph, if you like, is a foundation for AI-related activities. So for example, this is exemplified by, say, the data scientists developing new algorithms to utilize the graph from within their graph analytics environment. So as the graph gets richer, the data scientists can actually run complex graph algorithms on that data and actually derive new insights that can then be used to enrich that graph. So for example, what you could actually do as well is maybe, if you use a deep neural network, you can explain how, when, and where a decision-making process occurred, and also materialize how the decision was made. And then you can actually expose that to future similar searches. So again, things are learning over time. So it's just a couple of thoughts there. So what I'm going to do now is actually just walk you through a few ways of how to actually, people are using to enrich their graph, and also managing their data and searching their data. So first of all, the one that springs to mind a lot, and I'm sure all of you have heard of this, is natural language processing, and that is defined essentially as understanding human language. And what we actually want to get out of here is from unstructured strings representing language, we actually want to extract useful information. So what this actually happens is usually text is parsed using various parsing libraries, and entities are extracted, and as well as their attributes and the relationships between entities. Then there are a couple of things as well that play around with that, and one of them is named entity recognition. So this is a technique whereby you can actually identify the entity in a string, say in a sentence, and furthermore, a way to actually also categorize them. So, if depending on a particular sentence, you could infer that Daniel Craig is a person and he's also an actor. So it actually, starts to reify, if you like, these nodes and relationships. A couple of other things based on this are entity disambiguation. So I know that actually a lot of academic institutions are actually doing a lot of research into this. It's a very, very hard problem. And essentially what this is how to determine which entity is being referred to. So of course, you've got Amazon the rainforest, you've got Amazon the online store, you've also got Amazon, the tribal women warriors, I think, if memory serves me correctly, these sorts of things. How do you actually tell them apart? And that's actually quite a complex thing, and usually it's from the context to the rest of the text in which this is being referred to. And also sentiment analysis. So how do you actually identify that a statement? Is it a fairly polarizing statement? Is it a negative statement? Is it a positive statement? That sort of thing. So that also plays very much into this. Another tool, if you like, that we're seeing being used, or it's going to certainly start being used a lot, and in fact it's being it's being researched a lot in academia, is the idea of provenance and lineage of data. So certainly in the scientific domain, it's now getting very, very important to record data provenance. So you can't just say in a paper, oh, we discovered these results and that's it. You essentially really need to provide your raw data and step by step provide a description of all the processes that led to you taking that raw data and to deriving it further and further to actually eventually obtain your results. This goes towards also repeatable experimentation. So that's super important. And of course, these ideas are also very important in the industrial usage as well. Lineage as well as how data, what it may be snapshotting, versioning, what this data looked like 3 weeks ago and what it looks like now, and actually having links between the different versions over time. So that's also another aspect. So another way of actually enriching the data is, basically, there are two. So I'll cover the first one now, which is machine learning. And I just wanted to let you know that we provide, and this is free to use out of the box, at the time of writing, which was yesterday, 403 procedures and user-defined functions at the first GitHub repository. We just collectively refer to that as APOC. And these essentially are all sorts of functions and procedures helping you to integrate data, convert data, all sorts of graph algorithms. So please do have a look at that if you're interested. There's also a lot of documentation there, so you can actually see exactly what's being offered. We also then have graph algorithms library, and we actually are partnering with academic institutions on this to actually ensure that they're highly parallelized and therefore efficient, i.e. that they run really, really fast. And we've actually got graph algorithms covering the whole gamut. So, centralities, we've got PageRank, we've got betweenness, we've got a few of the others as well. Community detection, pathfinding, and all sorts of others as well. So again, if you're interested, please take a look at that repo. And again, these are available to use. And what I should also mention is that they're constantly being developed and refined over time. So we pretty much are trying to ensure that they're as good as they can be. So again, this is something we'd hope in the future that data scientists especially would find super useful, so engaging with them a lot more. The second way, so moving away from machine learning, is the deductive method. So this is from, say, a knowledge base, a rules engine, or an ontology. And I'm just giving you an example there of how you can actually, having a graph, how you can actually add more information to it to make it even richer. And that's, for example, if a node X has a person label, and it happens to have an outgoing teacher's relationship, then let's actually make X even more meaningful by adding a teacher label to X. So that X will now have a person and a teacher label. So if you recall at the beginning, I was saying that nodes can have more than one label, and this is certainly showing how that can actually work. So as you can imagine, over time you can actually add more and more of these rules to the application to enrich the graph. And in fact, continuing on this vein, basically, you can also hook into external data sources to obtain new facts. So for example, ConceptNet and WordNet actually have concepts, so that this would be sort of almost, yeah, not quite, but you can think of it as a category, if you like. And WordNet would actually have synonyms, antonyms, that sorts of things. So if in your domain you think a teacher and a supervisor, or a teacher and a lecturer, say, are the same thing, you can actually create a link between those two, so that no matter what search queries get posed later on in the future, they'd still get the same information, because in your particular domain, these two things are the same. And what you can actually also think about doing as well is using the graph to deduce a set of rules. So again, if you don't know what rules, you're starting off with the graph, you're not quite sure what the rules are, you can actually use the graph once it's got to a certain size to maybe come up with a set of very, very simple rules, and then use those to enrich the graph, and then subsequently enrich the rules as more data gets added. And you can imagine going on that this will be feeding back and enriching both the graph and the rules over time. So very, very importantly now, so we've actually looked at how you can actually enrich the data, and now I'm actually going to focus a bit more about how you actually search the data. And so this is something certainly I spend my working life on Cypher, so hopefully I've got some interesting things to say here. So just to introduce Cypher, it's a declarative language for property graphs, and what we do is we're seeing that as the SQL for graphs, and very importantly what we've done is make that an open language. So it's no longer Neo4j who decide the directions of Cypher, what new features it should take on. It's now an open process. So I'll share a link later on, so if you're interested in getting involved, please reach out to me. A very important thing for those of you who are not familiar with Cypher is that essentially pattern matching is the be-all and end-all in Cypher. It's the beating heart. What Cypher can do is obviously read data and update the graph. But from now on, I'm just making a note that I'll only be talking about the reading only part. Also, something else is with any serious query language, as some of you may know, actually getting a definition of the formal semantics is a very important thing. And what we actually are doing at the moment is collaborating with the University of Edinburgh here in the UK, and they actually are defining the formal semantics of Cypher. So it's actually going to be released at some point pretty soon, and we've actually submitted a paper as well on this. So the idea around here is to actually absolutely ensure the correctness of Cypher and make it a standard de facto property graph query language. So Cypher, how it looks like is pretty much all around the match clause. So you probably recognize again this drawing from before, but here what we've actually done is put Cypher around it. So pretty much you can see that there's a match. Then the first node is actually enclosed by round parentheses. So that's actually using the ASCII art. The relationship is enclosed by square brackets, and we're indicating a directionality by the arrow, and we're returning information as well. So that's pretty much what Cypher looks like. We obviously then have some bits that look a great deal like SQL as well. We've got order bys and where predicates and that sort of thing. But essentially what it's all about really is matching a pattern, and a pattern being defined as a node relationship node, and that can go on obviously for any number of variations. So here at the bottom I'm actually showing you a couple of ways in actually flavors that a pattern can take. So the first one is, for example, a node followed by a relationship, an outgoing relationship to another node, which is then followed by an incoming relationship from yet another node, node 3. So you can imagine actually chaining these up, it gets quite descriptive. What we also have is the ability to describe or express something called transitive closure. So the second one, where we have N1 knows N2. What that's going to do is it's going to fetch all of the knows relationships. So it will be, so say N1 is somebody called Dan, and he directly knows Anne. But say Anne knows Sally, and Sally knows Bob. That particular query will not only return Anne, it will also return Sally, and it will also return Bob for as many knows relationships as exist. So this is actually how you can get a friend of a friend of a friend of a friend, ... So that's actually quite a powerful construct. We also have a flavor on that, in that you can actually decide to constrain how many knows relationships you traverse. So for example, you can have N1 nose star 1 dot 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 3. So that will essentially say, give me at least one nose and at most 3 nodes. So that in that way you actually can get a friend of a friend of a friend of a friend of a friend, I think. Yeah. But anyway, you get the idea. So that's actually a super, super powerful way of actually expressing this. And this is something that's rather difficult to do in SQL, for instance. It can be done, but it's not quite as elegant or succinct. So down in the bottom right-hand corner, if that's actually our openCypher website, so I certainly urge you to look at that. But that particular link there to our references has a lot of the information I'm going to be talking about in the next few slides. So if you want more information, please take a look there or just reach out to me. But as I was saying earlier on, we actually are actively evolving Cypher. We think it's a fantastic language, of course, but there are many, many things that we can actually add to it. And this is all done within the openCypher implementers group. And as I've mentioned before, that this is an open body of collaborators. So some of us are in this group from Neo4j, but we also have a few researchers and a few industrial people as well. And what we're doing is meeting every so often. And the idea is to identify, design, and then feedback and iterate on new features that will make it into Cypher next year and the years to come. So what I actually want to talk to you is about the 4 facets that will actually are under discussion at the moment. Some are more ready than others, but the idea is that once the design for these have been finalized, they'll actually make it into the next versions of Cypher. And I need to emphasize here it's the next version of Cypher. It does not necessarily mean it will be implemented in Neo4j at exactly the same time. So maybe a bit of a gap. But as long as it's made into the Cypher, the query language, you can expect over time this will make it into Neo4j too. So without further ado, it's all about multiple graphs, complex paths, configurable pattern matching semantics, and constraints. And I'll just discuss each one of those very briefly. So I think it's fair to say we've spent most of this year actually defining how multiple graphs or query composition will work. And the drawing down at the bottom actually, I think, describes a lot of what this is all about. The idea is that Cypher currently operates on a single implicit graph, if you like. It's not a named thing, it's just, you know, the graph as such. And while that's a great thing, we've actually had quite a lot of feedback from customers and also, you know, looking into the future as well, that actually there would be a good use case for having multiple graphs. So, for example, the idea that you can create a new graph from an existing graph. You can also define views. So maybe you have your knowledge graph, for instance, but there may be some sensitive information in there. And what it is that you don't want that sensitive information to be accessed by any means by most of the company other than, say, the CEO. So View would actually help you to constrain that and to you know, actually ensure that that doesn't happen. Access control named queries. And so essentially what multiple graphs is all about is the ability in Cypher to accept multiple graphs as input and also a table as well, because sometimes we actually find that having a table can drive the generation of new graphs, but also for a Cypher query to return a multiple graph and also a table as well if you want. So this is actually very powerful. So as you may know in Cypher at the moment, we're only ever able to return data in a tabular format, right? So the idea is that we can actually return a graph, and that would be a super, super useful thing to do. With this ability, we've also defined the way a query can actually be chained to form a query pipeline. So you can imagine that your first query, you know, loads a graph from somewhere, and it's a named graph, operates on that, and creates a new graph out of that, returns it, and actually that gets fed into the next query, which then maybe does something slightly different to that. Maybe it takes this newly created graph and takes yet another graph that's stored somewhere else and integrates those two. So you can actually imagine chaining this actually starts to give you quite a lot of expressivity and power. We're also looking at subquery support as well. And I do need to mention this actually has already been implemented on our Cypher for Apache Spark system, the CAP system. It's just to show you what this pipeline composition would look like in a pictorial form. You can see that here we've actually got 2 queries. The first query accepts graph A and graph B as inputs. So these graphs already exist somewhere. They've been materialized on disk, and there's a way to actually reference or to, you know, address those graphs. And there's some table coming in as well. Maybe, you know, it's a driving table. It's got lead nodes or something that you want to manipulate. Anyway, that first query then does something. What it does is returns you a brand new graph called graph B prime, and maybe this is a subgraph out of A and B integrated together in some way driven by the table. That then gets fed into the second Cypher query, and using that, it actually returns to you yet another graph, graph A prime, as well as another table as well. So you can actually imagine how well this would sit, say, for example, in that AI workflow loop that I was talking about earlier, that subgraphs like this could maybe be handed off to the data scientists to work on further, and then they would, taking that graph, mutate it in some way using a graph algorithm, and then actually place it somewhere else for yet another query to pick up to add to the original graph. So much for multiple graphs. As I said, that's actually that's pretty much been our focus for the year. Another thing we've been looking at are very complex paths, so patterns of patterns. And this actually has a very, very long lineage in academia. So these sorts of queries have been studied for at least 30 years. So we're actually looking now at bringing this, this into the query language. And the idea here is that you can actually specify a path. So a path, remember, being a series of node and relationship node relationship patterns. So essentially what you can now do is you can specify that path by means of a regular expression of the relationship types. So what you can actually do now is actually start nesting patterns, which you can't do in Cypher at the moment. And what you can also then do is have node and relationship tests. So actually I'll probably just walk you through the example. It may become clearer then. So the query below, again, just don't worry too much about the syntax. That's still very much under discussion. You can see it gets quite complex. The idea here is that you can find somebody who's loved by somebody who's hated by someone you know. So what this pattern here is trying to describe is it's insisting that there's always a knows relationship followed by a hates relationship, that pattern as a whole occurs at least once. So that's the plus operator you see over there. That's taken from regular expressions. As you may know, this means one or more times. Then that as soon as you've had at least one of those instances, that there's a loves relationship, and then that is an outgoing loves relationship to someone else. And that's the pattern that would then be matched. What I mean by node and relationship tests on that is you can imagine these paths can get quite long. So you can actually match a path that has knows, hates, knows, hates, knows, hates, loves. What you can actually do is you can actually write tests that ensure that nodes that are traversed along the way in that path also apply to some predicate that you define. Maybe you want to check that between the knows and the hates, that the node in between those has a vehicle label or something like that. So you can actually imagine it can get quite powerful, very, very expressive. And I should also mention as well, we're also looking at being able to specify a cost function for paths as well. So a way of actually giving you the ability to define a shortest path query, for example, but based on some function that you think is important. So maybe it's based on a weights relationship a weights property in your relationships, that sort of thing. So that's still very much under development, but the documentation so far, as well as a lot of our talks and slides on this, are available at that URL I gave you earlier. So actually, running quite short on time, so I shall have to hurry a bit. The other thing we've been looking at is configurable pattern matching semantics, and essentially it sounds like quite a fancy term, but all that is pretty much extending the way a pattern matches. So those of you who know Cypher know that at the moment we actually have a default, and that is that in any path, no relationship can occur in that path more than once. So we don't ever retraverse the same relationship, essentially. So this we found actually works really, really well with our customers and in general. But there could be very, very, at the moment, corner use cases, but maybe these will grow over time, to actually have slightly different pattern matching semantics. So this is what we're actually going to be adding. And that is essentially also the ability to specify for a query that you also don't want a node occurring in a path more than once. So at the moment we do allow that, but maybe you don't want that. And also then to go completely in the opposite direction, we also want to add the ability to say that a path can absolutely contain the same node or relationship more than once, and that's perfectly okay. And that will return to you a few more results than you'd get at the moment. So bundled up with that obviously are studies into how this actually affects query running time. This is obviously very much a concern we have, is by adding these things we don't want to actually mess up the query time performance for our users. So we're actually also looking and considering that very, very hard. And the fourth thing that we're actually looking at are better constraints, and essentially, so you see quite a lot of things that you'd expect to occur over time, like cardinality constraints. So, for example, a node's relationship must occur, no more than 3 times between any 2 person-labeled nodes, or that a particular relationship type can only end at a label, say, labeled with node labeled with vehicle building and things like that. So you can imagine all the permutations. So just talk you very, very quickly through the eBay ShopBot example as a knowledge graph, exemplifying knowledge graphs. And again, they actually had a great talk at Graph Connect New York. So please do go online and take a look at that. It's certainly well worth watching. The idea is basically all about personal shopping, and the idea is that as you are there with your cell phone, you can actually converse with the ShopBot and by text, picture, and voice, and essentially the ShopBot then would send to you recommendations. And underpinning all of this, of course, is Neo4j, but also lots of natural language processing algorithms to actually make this work. So let me just walk you through a quick case study. So, you have that ShopBot now begins, right, what are you looking for? And then you would say, for example, I'm looking for a black Herschel bag for under $80. So, they're very specific bits of information encoded in that sentence. Okay, where should I focus? And actually, you can see in the middle image that already the ShopBot has been able to identify what this is. You're actually looking for a bag, and now it's saying what type of bag. So it's trying to drill down further and further into more detail. Unisex bags or handbags and purses, and so on. It's also very intelligent. It's actually able to parse images as well. So again, it's a very, very similar thing here. So just to show you very briefly how this works at a very high level, this is say a sentence that you as the user would pose, and what's actually happening here is it's parsing this language and actually breaking it up so that it actually identifies what the entity is, but also what the attributes are of the entity. What the color is and the material, the type, and the cost, things like that. So anyway, here's the a snapshot of the knowledge graph. You can imagine this thing is rather, rather large. And what it actually does is it's identified that this thing is a bag that you're looking for. So this is the starting point. And from there, what it can actually now do is, based on the other information, it actually uses these techniques to decide whether to go to the left, to the men's backpack, or whether to go to the right, to the handbag. And yeah, so that's essentially as a taster of what that does. And yeah, if you're at all interested, please do try it out. There's the URL. And with that, I'd like to thank you very much for your attention. And yeah.
Thank you so much, Petra. So we do have a couple minutes left, so we'll try and answer a few of your questions. If we don't get to your question, I'll do my best to email out a response to you after, so don't worry. So for Cypher composition, can you share with us some best practices for composition and possibly any good libraries that would facilitate composition?
So as to the latter, nothing yet exists to our knowledge, but if you have information, please certainly do reach out to me. Best practices, that's a really, really interesting one. So actually, so when I was talking about query chains, what I didn't mention as well is that we'd allow through subqueries also query trees in a way. Best practices, yes, we probably would have a few preferred ways of doing these things. Off the top of my head, I can't actually think of what those may be. This is something we actually do need to drill down into, but this is certainly a very good point, and I'll make sure that we actually, with this, add documentation about that. So that's a great question. Thank you.
Great. And is it possible to write Cypher query in SQL servers directly?
So to my knowledge, the only place, no, not in, you mean any relational database, or you're talking about Microsoft SQL Server? I'm assuming you mean any relational database. No, you can't. You actually need, there needs to be a layer available to actually allow you to do that. So for example, that's what the agents graph people did. I think they're a South Korean outfit. And what they actually did was they wrote a Cypher query engine on top of PostgreSQL. But no, you can't actually use Cypher in a SQL query directly, in a SQL database directly. So the next question, oh, this is a good one. Is it possible to record the history of the application of labels to a node, i.e. this node was labeled teacher between this date and that date, but is no longer labeled that today? Yes, actually, that's a fabulous question, because we're actually in talks with a researcher in the States about temporal graphs. So this is yet another direction we're exploring, and it's precisely this sort of ability that multiple graphs plus will give us. By plus, I mean we start off with multiple graphs, but then we add all sorts of other things on top of that, such as snapshotting and this temporal nature. So if you go to that references page I sent, I linked on my slide, there's actually a bunch of academic papers on there. And in the first section about property graphs, there's one about property graph extensions, and that's all about adding temporal constructs to the property graph. And in fact, that research is exactly doing that sort of thing. What this entity or node look like between these two data times, and at what point were things changed. So it's very much something we're going to be looking at in much more detail. But as I say, the paper is out there, and certainly I recommend you read that. So there's one here, so probably this will maybe be the last question owing to time, but so there's one about the fact I mentioned a single database for graph stitching is supported. What about stitching across silos? Do you have tools for that? So as mentioned, we do have tools to actually bring in or suck in, if you like, relational data from a relational store, and we also have the same for CSV files as well. So I think the idea there would be that you'd actually import all of your relational data, all the bits of your relational data that you're interested in importing, I should say, into your graph, and then additively add other sources, either whether these are from CSV files or from other relational databases after that fact. And what you'd actually then do is after each import is ensure that you write some logic to actually stitch these together. So what is maybe a customer in one database is maybe known as a buyer in another database, and you'd actually write some logic to kind of merge those two together. And in fact, Cypher allows you to do this very easily. The fact you can actually merge on patterns, which means it will either create or update data if a certain pattern is found. So yes, that can certainly be done.